Uh, in the same sequence of problems on measurable sets and properties of the outer measure, in the first question we are asked to show that if we have a set which has an outer measure, so we have A, subset of R, and we assume that the outer measure of A is finite. I'm sorry, not equal to 0. Okay? So what we want is, we want to show that in fact there exists a subset B, subset of A, which is bounded. This is the key. This is the difference here. Okay? Such that the measure, the outer measure of B is also greater than 0. Okay? So one way to look at this, and including the second problem, in fact, is to use a property of R. So we have R, and there are many ways that you can have R as a union of intervals. Okay? So union of, they can be open, closed. Okay? And for example, we can take the union of minus k, k, k. If you want them to be, let's say, disjoint, we can have them as the union, the union of k, k plus 1, k and z, okay? Uh, we can have them intervals of fixed length also. That can be done. So instead of having k plus 1, we can have k plus, so in other words, uh, we can have, this is the real line, and you start, for example, at fixed delta, and you go from 0 to 1, just to give an idea here. So we can divide this interval into n intervals of length delta, and you proceed by translating this over the entire So this would be, of course, delta to delta, etc., etc. So you take the intervals. So if you call them xi's, you consider xi's plus 1, and over the interval 0, 1. Okay, and then, so they are finite. And now what you do, you consider a translation of them by taking plus n. So you take n plus the xi's. So these i's, of course, are between 1 and k. And now you consider these intervals n plus xi plus 1. And you take the union of all this over n and I. Okay? N is in z, and I between 1 and k. So this will give you um, intervals, countable intervals that will give you the entire R, and they are all of fixed length. I mean, not fixed length, but length less than delta. Sorry, less than delta. In any case, so it depends on the question at hand. So for example, if we look at the first question, so we can just take the ICA, for example, bounded. Okay, so here we take R is a union of I, N, and we just assume that INs are bounded intervals. Okay, so in this case we know that A is going to be the union of A intersect the INs, and we know also that the measure of A by the subadditivity will be less than sigma of the measure of A intersect IN. So what happened? If all of them, so since this one is greater than 0, okay? So we know that there exists an n0 such that the measure of A intersect in0 will be not equal to 0. Otherwise, if they are all equal to 0, you're going to have this one equal to 0, and therefore we get our contradiction. So this set here, okay, so this set is our set B, which is a subset of A, and its measure is not equal to 0, and it is bounded because it's a subset of in0. Okay, so that's one way to see it. Now for the second one, we assume that A is measurable. Okay, and we assume that its outer measure is finite. Okay, so fix epsilon. Okay, so now what we want is use the argument I said earlier, that we can find R is equal to a union of intervals, okay, disjoint intervals, such that the length of each interval is less than epsilon. Okay, and now same argument gives me that A is equal to the union of A intersect the INs, and because A is measurable, then the outer measure of A is equal, because they are all disjoint subset. In is measurable, it's an interval, so its Borel set is measurable. A is measurable, the intersection is measurable, and therefore this is equal to, and this is very interesting, okay, otherwise we only have what? We only have the subadditivity of the outer measure, but in this case we do have the equality there. Therefore, since the measure of A is finite, this will be finite. Therefore, the series is convergent, and what we have is that there exists an n such that, okay, sigma of the outer measure of A intersect I n for n greater than n, okay, this will be less than epsilon. Okay, so what we are going to do is to consider A1 equal A intersect I1, and A2 equals A intersect I2, A intersects, sorry, okay, so In minus 1 equals A intersect I n minus 1, and the last one, An, is A intersects, or the union of I greater or equal than n. Okay, so we know that the measures, the outer measure of AI's less or equal than the outer measure of II's less than epsilon. This is for I from 1 to n minus 1. As for the last one, the measure of An is going to be less or equal than sigma of the measures of A intersect the I mean it's equal in fact, because it's measurable. So I greater than n, which is less than epsilon. Okay, and it's easy to see that A, which is the union of A intersect i's, is equal to A1 union A2 union A sub n. So we have what? A, which is a finite union of sets with all outer measure less than epsilon.